Alright, so I left this as an exercise. The steps are similar. There will be some cases and so on probably, but it is similar. Okay, I will leave it to you. And you may ask such things, work on this problem, this exercise, and if you cannot come up with the result, you may ask it during the office hour or some other time. I may give you some hints and so on, but first try to do it yourself. Okay. All right. Now, as a uh, as an application of this, we can, for example, compute such limits. Okay. Uh, compute the limit uh, as n goes to infinity. Okay, n squared plus 1 divided by 2n squared plus 3n plus 4. Now, of course, you know how to compute this limit, right? It is just 1 over 2, but we have to do it so that, we can, use all the facts we proved so that, we will have a proof of this. That the limit is equal to 1 over 2. How can we do this? You see, start with this. Divide both sides with n square. So I will get 1 plus 1 over n square. Since I am talking about limit as n goes to infinity, I may assume that n is positive, okay? I divide numerator by n squared and let's divide denominator by n squared. So we have this. Now you see I have several terms and summations and then I have a division. Okay, well, we proved that we have proved earlier that, right, that was actually the first thing maybe we proved is limit limit of 1 over n is 0, right? We proved this. Well, then I have, you see, several terms involving 1 over n. 1 over n squared is just 1 over n times 1 over n. Hence, the limit of 1 over n squared, well, this is just 1 over n times 1 over n, so this is just 1 over n times limit 1 over n, and this is 0, and the other one is 0, so this is 0. And then I have limit 3 over n. This is just limit of 3 constant sequence times limit of 1 over n. What is the limit of the constant sequence? Well, it doesn't go anywhere, so the limit is just 3, right? You may also prove this, why the limit of a constant sequence is just that constant. And limit of this is just 0, so this is 0. Limit of 4 over n squared. Well, this is limit of 4 constant sequence times limit of 1 over n squared. We already proved that limit of 1 over n squared is just 0, and this has limit 4, so this is 0. And then I have sums of these terms. I can write this, step by step, but let me just do it as follows. We know that this has limit 1, this has limit 0, this has limit 2, this has limit 0, and this has limit 0. So uh, sum of limits, right? I have two convergent sequence. Their sum will converge to 1 plus 0. And here this will converge to 2, 0, and 0. So the numerator will converge to 1, denominator will converge to 0. And I have two convergent sequences, and the limit is not 0. I can divide with this, and I get 1 over 2. Okay? Actually, I just do the following. This divided by this is equal to this times 1 over that sequence, okay, 1 over this. And when you have 1 over something, you have just the limit will be just 1 over the limit of the original sequence. So this is what we get. Any questions so far? Sorusu olan var mı? Peki. Bakalım başka ne varmış. Okay. There is this fact stated in the proof in the book proposition. Let me also cover that. It says the following: every real number is the limit of a sequence of rational numbers. Well, this is actually an obvious fact, right? Every real number is the limit of a sequence consisting of rational numbers. Why is that? Well, it is because of the following. Uh, you know, first let me give an example. Say our real number is like this. 27.018359600 and so on. Okay, it's a real number. What is the sequence consisting? How can I find a sequence of rational numbers converging to this? Well, it's very easy. So let's choose x1 to be 27, x2 to be just 27.0. Well, it is again 27. x3 is 27.01. x4 is 27.0. Oops. 18, and you see how it will go. I'll just each time take another digit from the decimal expansion of the real number. You see, by construction, all these are rational numbers, and you just keep taking more and more digits from the decimal expansion of x, and clearly this xn, the sequence xn will converge to x. Okay, that's the idea. But how can we write this down? We did actually this, the existence of decimal, real numbers. How was it? Recall that we have proved the existence of a sequence of rational numbers what was it, şöyleydi değil mi? Onu buraya yazmamışım. Nasıldı? R, R1, R2, Rn, so that bu Rn'ler increasing'ti, right? R1, R2, R3 and each Rn was less than x and x was less than Rn plus 1 over 10 to the power n, right? For all n. 1, 2, 3 and so on. Oops, sorry. Bir dakika, ekran. I lost the screen. Okay, here it is. Okay. Okay. So you see from this the difference. Okay, here is x, here is Rn, and here is Rn plus 1 over 10 to the power n. So you see that the distance between Rn and x, so it is this distance, is less than this distance, and this is less than 1 over 10. So hence x minus Rn is less than 1 over 10 to the power n, right? Yeah, maybe I should choose like this. And you see 1 over n, 10 to the power n gets of course smaller and smaller. So given epsilon positive, okay, choose n 0 so that 10 to the power n 0 is larger than 1 over epsilon. I can do this because 10 to the power n 0 is larger than n 0, and right, you can prove it easily, and the set of natural numbers is unbounded, therefore 1 over epsilon cannot be an upper bound for natural numbers. So we have this. Okay, so if n greater than n0, then x minus Rn, which is less than or equal to this, but n greater than n0 implies this is less than 1 over 10 to the power n0, Uh, yes, because 10 to the power n is larger than this, therefore this is smaller, but this is already less than epsilon. Okay, so we are done. So we have this. Okay, given epsilon positive, we have some n0, and if n greater than n0, then this thing is less than epsilon. Okay. So every real number, okay, every real number is the limit of a sequence of rational numbers. This is of course, obvious because rational numbers are everywhere, right? We know that in any interval you can find a rational number. Therefore, they are dense. They close to every real number. Okay. Now we will introduce a new concept, so-called accumulation points. Maybe you have seen this before, but uh, we will see it in more detail, possibly. Accumulation point. Evet. Uh, there are uncountably many ways of, there are uncountably many sequences that converge into a fixed real number. Consider zero. What are the sequences that converge to zero? Uh, there are, many ways, uncountably many ways. Uh, yani e, dizi oluşturmanın hani burada çok böyle nasıl diyeyim katı bir kuralı yok. E, Yani size bir sayı verildiğinde işte 1 ile başlayın. Buradan bir reel sayı seçeceksiniz, değil mi? A1 diyeyim. Sonra 1 bölü 2 yarıçaplı yuvarı alın. Buradan bir başka reel sayı seçeceksiniz. A2. Dolayısıyla yani her seferinde işte mesafeyi 1 bölü 3, 1 bölü 4 diye kurun. 1 bölü yani bunlardan birer sayı seçiyorsunuz. Bunlar otomatikman bu değil mi, merkezdeki sayıyı convert edecekler. Kaç değişik şekilde seçebilirsiniz? Buradaki sayılar kadar değil mi? A1 seçimi var. Onun koordinatı R'ye eşit. Sonra buradan kaç çeşit seçebilirsiniz? Buradaki aralığın onun da koordinatı R'ye eşit. Dolayısıyla sonsuz tane R'nin çarpımı kadar seçim imkanınız var. O da oldukça hani büyük bir küme. R'nin kendisiyle sonsuz defa countable product'ı. Ama sonuçta o da sanırım countable bir pardon yine R'ye koordinatı R'ye eşit olan bir şey olacak ama uncountably many ways var yani. Tamam mı? Yani bir tane yok. Bir tane yok. Ama hani ne kadar var? İşte uncountably many ways. Yani çok fazla. O aslında şeye denk geliyor. Yani bir yerde o muhtemelen bütün convergent dizilerin şeyi kadar var yani. Nasıl diyeyim? Kardinalisi kadar. Peki accumulation point and theorem of Bolzano-Weierstrass onu göreceğiz. Önce accumulation point nedir onu tarif edelim. Let S be a set of real numbers. Real numbers. A real number. A real number. A is called an accumulation point of S if the following happens: if for every epsilon positive, the interval a minus epsilon, a plus epsilon contains infinitely many points of S. Okay, so that's the definition. So let me try to explain this on a picture. So this is the, let's say, the real axis, and I have a set S. A real number A is an accumulation point of this set S if the following happens. You give me an epsilon and I draw the epsilon ball or interval about this real number. Then in this interval there should be infinitely many elements from S. Okay, so there should be infinitely many elements from S. If you give me another epsilon, possibly a smaller epsilon, then I have such an interval. This interval also should contain infinitely many elements from S. Okay, this should hold for all epsilons. Let's say this is epsilon 1, and then I have a plus epsilon 2, a minus epsilon 2. For each epsilon, this interval should contain infinitely many elements from the set S. So S is something like this. Okay, each interval containing A should contain infinitely many elements from S. Let's see some maybe examples. Uh, okay, I'll give in a minute an equivalent statement. Uh, uh, okay, let me just first try to explain this on examples, and then I'll give an equivalent statement. Maybe that will sound more familiar to you. Okay, let's for example consider this set. So it's open here, closed here, and then I have this 2 here. Okay, now what are the accumulation points of this? So the question is, what are the accumulation points of S? Efendim? Ee, Yok. O equivalent statement'ta var. Hani vereceğim o statement'ı ama ilk önce bu tanımı bir anlayalım. Olur mu? Bakın şimdi ben size şeyi çizeyim. Okay, so this is our set S. 0 is here, 1 is here. So my set is this. interval, and then I have also 2 here, right? This is S. Now let's see whether the following real numbers are accumulation points or not. For example, let's consider this point, and then I have, let's say, this point B, I have this point C, D, and I have also this point E. Okay, let's see whether these are accumulation points or not. Pictorially, okay, let me choose a different color. Okay, now pardon, let me make this a bit longer. Now I choose a different color. Yes, this real number is not an accumulation point for S. Why is that? You see, if I choose an interval like this, right, this interval contains no points from S. Therefore, A is not an accumulation point, right? So this is not an accumulation point. Let me put an cross here. What about B? Well, whenever you draw an interval around B, an epsilon interval, that interval will contain a part of this interval 0 to 1, and this interval of course contains infinitely many elements. Therefore, B is an accumulation point. The same thing happens here, right? Any interval containing C will contain infinitely many elements from S. So that's also an accumulation point. And similarly, if I draw any interval here, it will contain again infinitely many elements from S. So that's also an accumulation point. What about this? Well, any interval from this contains elements from S, but each time, not each time, if you choose bigger epsilon, of course it contains infinitely many, but if you use small epsilon, then this interval contain only one element from S. Therefore, E is not an accumulation point because every interval should contain infinitely many elements, and this two contains only one. So this E is not an accumulation point. The set of all accumulation points, the set of all accumulation points of S will be denoted as S prime. We will either call this the set of accumulation points of S, or and called the another name is derived set of S. And in this case, what is the derived set? S prime S prime in this case, well, anything between 0 and 1, including 0 and 1, right? These are accumulation points, and 2 is not an accumulation point. So the derived set is this. Is this okay? Now let me okay, go ahead. Evet, evet. Okay, you are right. Now the an equivalent statement is this. So let me give also that statement. uh, equivalent statement. A real number uh, A is an accumulation point if what happens, accumulation point of S, if the following happens, if A minus epsilon, A plus epsilon minus A, right? I delete the center of this interval and take the intersection of this with S is not empty. I guess this is the statement you remember, right? From previous courses, possibly. Uh, in other words, any deleted neighborhood of A, any deleted interval containing A contains at least one element from S. These two statements are equal, right? Because if each deleted neighborhood contains one element from S, then every interval contains infinitely many elements from S. Why is that? You see, A is here, and I have this interval, uh, and this tells me that uh, this interval contains an element from S, but that element cannot be A. So there is some, let's say, S1 here, okay, from S. And then I do this. I choose a smaller interval. Since S1 is not equal to A, I can choose a smaller interval excluding S1. And then I repeat the same argument. This interval contains an element from S which is not equal to A, because A is an accumulation point. So there is some S2 here. And since again S2 is not A, I can choose a smaller interval, leaving S2 outside, and choose another element S3. And this way you see I find a sequence of elements which are all distinct: S1, S2, S3, S4, and so on. So I construct an infinite set inside this, inside this interval. Therefore, any interval about A contains infinitely many elements from S. That's the basic argument why these two statements are equivalent, okay, for accumulation points. Does this make sense? Mhm. Let's do another example. Let's, for example, take S to be, first of all, a finite set cannot have an accumulation point, right? By definition. Why is that? Because, if something is an accumulation point of, some set, any interval about that claimed accumulation point should contain infinitely many elements from that set. But if the set has only finitely many elements, that will not be possible. Therefore, any finite set has no accumulation points. However, having infinitely many elements doesn't also guarantee that the set has an accumulation point. For example, let's choose S to be the set of integers. What are the accumulation points? For Z, can you tell me what is S prime? The set of derived, accumulation points. Yeah, it is empty, right? Because you see, 0 is here, 1 is here, 2 is here, 3 is here, -1, and so on. If you give me any real number, A, either here or here, right? I can always draw an interval, a small interval like this, and that interval will contain at most one integer, right? Yeah. Therefore, S prime, therefore A is not an accumulation point. Therefore, S prime is empty. I could write an argument like this. Let A be any real number, then A minus 1 over 2, A plus 1 over 2, intersection with Z, right? This interval has length 1 unit. Therefore, it can contain only one integer because the distance between two integers is at least 1, right? So then this set uh, can have at most one element. So it cannot be infinite, and thus A is not an accumulation point. Right? Hence, uh, Z derived set of Z is empty. What about this? Let's say, let's choose S to be the set of rational numbers. What about the derived set of this? What are the accumulation points of Q? R, yes, because we actually just showed that any real number is a limit of a uh, or okay, there are many actually arguments. If you choose any real number, then consider this interval a plus epsilon, a minus epsilon. This interval contains okay, I can do this. This interval contains a rational number, right? Well, actually, uh, okay, there's a evet, right. This interval contains a plus epsilon contains a rational number. Let's say R1, right? R1 is larger than a and less than a plus epsilon. And then I do this. I look at the interval a R1, and again by the density theorem there is some R2 greater than a and less than R1, and then I look at this interval and choose R3 greater than a less than R2. I do it this way so that R1, R2, R3 are all different. Right here you see I have this R1 is larger than R2, R2 is uh, larger than R3, and so on, so that these are all different elements, uh, and therefore uh, S or Q, okay, sorry, so Q intersection with a minus epsilon, a plus epsilon contains the set R1, R2, R3, which is infinite. Or maybe we could use the equivalent statement. What was that? For a real number to be an accumulation point, any deleted interval should contain an element from that set. And if you choose this interval, a minus epsilon, a plus epsilon, this interval clearly contains one element, rational number, and this rational number is between a and a minus epsilon. Biraz ters oldu. A minus epsilon, a plus epsilon. Therefore, this R lies in the deleted neighborhood, right? So this is a minus epsilon, a plus epsilon, intersection s minus a. So this lies in the deleted neighborhood. Therefore, it's an and this implies A is an accumulation point of S. But A is a arbitrary real number. Therefore, hence the set of accumulation points of Q, the derived set of Q is just R. Okay. Okay, I have only 5 minutes. Okay, let me stop here.